Alright, thanks for joining us for this fourth video in chapter 5 about stereochemistry. Now that we are armed with the way to assign absolute configurations in terms of R or S to each chiral center, it's maybe a little bit easier to think about diastereomers. Right, like these, there's two types of diastereomers. There's the geometric isomer type, and then other diastereomers. So these are known as transverse geometric isomers. And those are a type of diastereomers. And then here are sort of the other types of diastereomers. Okay, how do we know that something is a diastereomers? One way to define them is they're stereoisomers of each other, but they're not mirror images of each other. Another way to think about that, that's equally true, is diastereomers have two or more stereocenters and some of those diastereomers, not all, some stereocenters have the same configurations. But the rest are different. That's really maybe the most that's probably the most comprehensive, best way to define diastereomers. And why do we care about diastereomers versus enantiomers? Well, diastereomers, they can have different physical and chemical properties. Right. So they're like really different shapes and whatnot, right? Whereas you can imagine mirror images, enantiomers, they actually have the identical physical and chemical properties. And so for that reason, that distinction is important. Diastereomers can be separated from each other by things like chromatography, which I think you're learning about that in your lab class, chromatography or crystallography. Okay. Now, let's go back to this. How do we know these are diastereomers of each other? Well, let's look at the the stereocenters. Here's one. How do I know that's a stereocenter? If you swap two groups attached to the stereocenter, you become the other stereoisomer. Like if you swap this hydrogen and the methyl, right, like you become this molecule. And so that's a stereocenter, sorry. The same with these two, right? And you notice that one of the stereocenters have the methyl group pointing in the same direction, whereas the other stereocenter have it the other way. So this fits the definition of diastereomer or diastereomers because they have two stereocenters and one of them is the same, the other is different. So that fits this definition. What about the other one, other pair? Here's one chiral center, here's one chiral center. Remember, chiral centers are a specific type of center, right? And then here's a stereocenter or a chiral center. And you notice that one of the stereocenters is identical between the two molecules while the other one is different. So that makes these two diastereomers of each other. Okay. And we'll come back to this idea that the diastereomers can be physically and chemically they have different properties, and so that you can separate them. And that's going to be a key idea we're going to talk about a little later. Okay, so please remember that. But let's think about another type of sort of stereoisomers that are of interest, and those are meso compounds. And these are pretty weird molecules that have chiral centers, and yet they're not chiral. So they're achiral, as in not chiral. So just because you have a chiral center doesn't automatically make you a chiral molecule or an object. Here's a case in point. This is dichlorocyclohexane, right? Like if you think about the mirror image of this, that we can draw, that's the mirror image. Now, I hope this makes sense to you, and if it doesn't, you can make molecular models of both of these molecules. This, if you rotate it around, kind of like rotate it around, right, that's the same as the original compound. And so for that reason, this molecule is actually not chiral, even though it has a chiral center. Indeed, these are the chiral centers. Because it has chlorine, hydrogen, and this methylene, and this carbon with a chlorine on it. So there's 4 different things attached to this carbon. So it is a chiral center, and yet it does have plane of symmetry. Which makes it not chiral. You might call that achiral, not chiral. And therefore this molecule is not optically active. Chiral objects or chiral molecules do not have a plane of symmetry. And here's another good example of meso compound situation. This compound. Now, on a casual glance, it may look like there's no plane of symmetry because it seemed to be cut the molecule in half right here, because there's bromine and here's bromine going back and looks different. But I want you to picture rotating this bond around so that we could draw this molecule in a different conformation like this. And if you don't believe that these two molecules are the same, you could build this model and see if it matches with that structure, right? And this obviously has a plane of symmetry, and so for that reason, this is also these two are called meso compounds. They're not optically active, they're not chiral, even though they have chiral centers. One of the ways you could figure this out without drawing or a molecular model kit is to name the molecule. Like if you name this molecule, right, assigning R and S, I hope it makes sense that the first one here is 1, 2, 3 R. So this molecule is 2R, 1, 2, 3, 3S, 2, 3 dibromo, butane. And but you can also, right, like go started from the other side of the molecule and counted 1, 2, 3, 4, and in that case it would have been 2s3r, 2,3-dibromobutane. So it's actually ambiguous which way you should number and how you should name this molecule. In a case like that, you should suspect that the compound is a meso compound, and indeed this is properly named. Instead of saying 2r or 2s or 3s or 3r, meso 2,3-dibromobutane is the proper name for that because it is a meso compound. Hope that makes sense. Now, another thing we could do with describing multiple chiral center situations, these guys notice they have multiple chiral centers, and that's why they can be diastereomers or meso compounds depending on the exact structure, right? When you have multiple chiral centers, it's really sometimes useful to draw them as Fischer projections. I personally don't necessarily prefer that convention, but especially when it comes to carbohydrates, carbohydrate molecules, the way the molecule structures are depicted is often using Fischer projection. And so for that reason, I want you to be able to be familiar with that. You'll see a lot of these in biochemistry classes in the future. The Fischer projection, the easiest way to think about this, if I convert this molecule, by the way, that's called lactic acid, the stuff that accumulates in your muscle when you have when you do a really hardcore exercise, we could redraw this as this structure here. Okay, and that's the Fischer projection. Actually, I might want a little more space than that's all. That's the Fischer projection. And how do you understand this? Well, the vertical lines are understood to be curled backwards, kind of like the curled backward shrimp. And that's what I imagine, but maybe that doesn't make sense to you. Now that I said it out loud, it doesn't quite make sense either, but you could understand the vertical lines to be curled backwards, okay? And then the horizontal lines in the Fischer projection, they're pointing toward you as though they all wanted to hug you or something. So when I think of Fischer projection, even though it may or may not make sense to you, I think of a shrimp that's curled backwards, not forward, and like a sticking out their little legs to try to hug you, right? Like they're pointed towards you. So the basically the picture you'll want to be thinking of for this molecule, the top and bottom groups, the vertical lines are curled backwards, and the horizontal lines are pointing towards you, like so. And you notice that's the exact same structure as that lactic acid, so that's the structure there. Okay. Indeed, like let's think about some other example, like if you had this Fischer projection, could you redraw this in the regular zigzag wedge and dash notation? Well, this is the same as, right, like the vertical lines are going away from you, and the horizontal lines are pointing towards you. So that's the actual structure of this molecule. And one way to do this, again, easiest way to do this is just to use a molecular model kit and build this. But like if you rotate this bond around, and if you sort of imagine looking at it perhaps from this direction, if this is your eyeball, hope it makes sense that you could, once you rotate this bond around, you can make it a zigzag form, and the first chiral center here, bromine, is going away from you. The second chiral center, bromine, was coming towards you, but then you rotated this bond around, so now it's going in the back. So this is the same structure, which, depending on from which way you're looking at, you might imagine yourself looking at this molecule. You could have drawn like this as well, but that would have been still the same molecule. Okay, now hope that makes sense. And as we said, that oftentimes the carbohydrate molecules are drawn with Fischer projection like this. So here's an example of a carbohydrate, and I'll let your biochemistry professor tell you what makes this a carbohydrate molecule. I wish we had time to cover that, but needless to say, each carbon has an oxygen on it. That's a carbohydrate molecule. And because carbohydrates come in all kinds of different stereoisomers, and that's why people like to use Fischer projection. Like if you have an enantiomer, it's easy to draw the enantiomer, easy enough. You just have to imagine the mirror right there and draw the mirror image. Okay, and then that would make these two indeed enantiomers of each other. Okay, and if you change just one stereocenter, you are making, hopefully you guessed it right, a diastereomer. Right, like these two are related as, diastereomers of each other. And you can even draw the mirror image of this. And of course these two are now related as enantiomers of each other, and in the kitty corners these are all related as diastereomers. Okay, same with this. Here's a good test for you. See if you can translate one of these into the sort of regular zigzag, wedge, and hash notation. Maybe stop the video and see if you can do it. The easiest way to think about this, if you don't want to make a model, is to imagine looking at it from one direction and rotating every other bond so that it forms a zigzag. So this, for instance, would look like so there's a total of 1, 2, 3, 4 carbons in the chain. 1, 2, 3, 4 carbons in the chain. In the end, we have OH group. I kind of did this upside down, but so this should be the structure, but you can build a model to verify that. Okay, and then this is really one of those things that really just takes some practice getting used to. This is the same as and that might have been the way you kind of imagined looking at it, but anyway, we'll do some practice in class, I'm sure, in the homework, so I'll see you then.